evaluation on the impact of interdisciplinary fields. Considering the population size, sampling is very important to our statistical analysis. We need to create a sample that highlights the key features of the population. The impact matrix, which measures the average allometric score of each interdisciplinary field, is calculated. The next step is to extract information from the matrix and run data clustering algorithm. In this way, the classification table, which matches different allometric score ranges with different levels of impact, is created. Eventually, we combine the classification results and the matrix. In order to attain a 99% confidence level, as well as a 1% margin of error, we used a sample size of 16,095 scholarly articles. This sampling technique was created by a simple random sample. This makes our data statistically significant.
So there are 30 subjects in total, and because there are 30 subjects, we have created a 30 by 30 matrix, and we give each subject an ID between 0 and 29, and having the 30 by 30 matrix allows every single possibility of 2 subjects to be calculated. For the purpose of convenience, we also do it so that it's symmetrical and we can get rid of half of the matrix. And when we extract the non-zero entities, that's what we use for the clustering algorithm.
There are a lot of clustering algorithms, but we choose k-means clustering because of its simplicity and efficiency. In a lot of cases, hierarchical clustering, a bottom-up approach, is portrayed as a better quality clustering algorithm, but it is limited because of its quadratic time complexity. In contrast, k-means top-down solution and its variants have a linear time complexity. It is relatively easier to implement, and the algorithm selects k initial clusters centers and iteratively assign each point to the closest centers and update the centroids until convergence. The specific algorithm we have applied is called k-means++, which accelerates the convergence by assigning initial cluster centers as far as possible. Note that we did not apply the clustering algorithm directly on the original data set. We applied the clustering on the matrix data, which was basically the average scores. The original data distribution, as you will see later, is heavily left-skewed, and experimentally, k-means clustering does not work so well on splitting a compact cluster within a large field.
So this graph, it shows the score distribution of all the allometric score data, and the y-axis is the percentage or the frequency of the papers, and the x-axis is the score. So you can see that there is a large portion of the papers that is a very low allometric score. Actually, 63% have a score of 2.25 or less, and only 15% have a allometric score of greater than 10. The highest allometric score is approximately 2,500, and you can see that there is a very low frequency for that high of a value. And this is another representation of the same thing. It's a bubble graph. So the y-axis in this one is just the pure allometric score. The x-axis is just a ranking from the lowest allometric score to the highest allometric score in a linear fashion. And the size of the graph, the size of the bubbles represents how many papers are in that specific allometric score. So as you can see, the first 2 allometric scores, which are 0.25 and 0.75 on the very left hand, have the most massive bubbles because there are so many papers in that field. And if you look on the very right, for fields that are about 2,500, you can barely see the dots because the frequency is so low.
So using the allometric scores, we were able to classify the different levels of impact. As you can see from the graph, if there is an allometric score between 0.25 and 3.61, the level of impact is to some degree. To have an adequate level of impact, you would need a score from 3.62 to 7.8. To be competitive, you need a score from 7.81 to 15. In order for an allometric score to be highly impactful, it would need to be from 15.01 to 31. However, in order to be extremely impactful, it would need a score greater than 31.
So this is the list of all the 30 subjects that are in our study, and you can see they're very color-coded based on the previous rankings. So the only really extremely highly impactful one is the general one, and the rest of them are mainly impactful to not very impactful. And this individual, because this is not interdisciplinary, this is individual, just that one subject, and we can use that to compare it between the interdisciplinary field between two subjects and the individual field. And that's going to be very important later.
Specific details regarding the extremely impactful results show that if the total number of publications do not meet a certain level, a high average score can be due to one or a few extremely highly scored papers. The paper, in this case, 3-year retention of radioactive cesium in the body of topical workers involved with the Fukushima Daiichi nuclear power station accident, scores extremely high, and that makes the average score in this interdisciplinary field between physics and anatomy and health professions extremely high. However, let us take a moment not only to consider this interdisciplinary field, but also to reflect on the allometric data itself. The question is, does this paper gain such a high allometric score because of the intrinsic value, academic value it has, or does the way allometric works also play a role here? As we all know, allometrics is based on social media platforms, and as commercial providers, many services in the social media, such as Twitter and Facebook, have a large stake in as many people as possible communicating as often as possible via their portals. A lack of communication or an unwillingness to communicate could result in the portal's failure to thrive commercially. So far, there's still no empirical studies to investigate how much bias can potentially be created because of this promotion of information. After all, traditionally, scientists are not encouraged to cite as many as possible. We therefore believe that our research studies, to some degree, are also a critical assessment of the allometric data itself. So here are the interdisciplinary fields that are considered to be highly impactful using our impact classification table, and more comparisons and connections will be made later.
So we've seen the extremely impactful and the highly impactful indexes, and this is going to just be a graphical analysis of it. So it's again another bubble chart, and the y-axis is the impact score. It starts at 14 and ends at 31, and that is for the highly impactful score. And there are two factors here. So the ones that have a high score are higher up on the graph. For example, biochemistry, genetics and molecular biology, and nursing. Those two fields have a really high score of almost 31, and they are very impactful. However, there's another factor, which is the size of the bubble, which is the number of papers that are published between the two subjects. And if you can see, medicine and nursing, which is on the bottom, has a very large bubble, which means there's a lot of papers on them. So it can show that there is a difference between the number of papers and the popularity of a certain interdisciplinary field and the actual quality of the papers. And this is another graph of the same thing, just spread out on the x-axis so you can see the bubbles more clearly. Okay, so we can make 4 conclusions with this data. So the first one is going to be regarding the tables. So you can either have weak or strong individual subjects, and they can make a strong or weak individual field. If you have strong subjects, they can make a weak interdisciplinary connection. And if you have 2 weak subjects, they can make an extremely strong interdisciplinary connection. It doesn't really matter. For example, nursing and medicine, they're both very strong and they make a strong connection. And mathematics and environmental sciences, they're very weak both, but they make a very strong connection as well. So that is the first conclusion. The second conclusion is that many unexpected correlations are made. For example, environmental science and computer science, you wouldn't expect them to have a very strong correlation, but they actually do. And further research would show that they do. The third one is, of course, as the bubbles get higher, the impact score decreases, or the impact score increases, but the bubbles get smaller. Of course, at a higher impact score, you're going to have less papers at that high level. And the fourth one is that the subjects that are expected to be closely related generally have bigger bubbles, but not necessarily more impactful ones than the other ones.
So for the discussion part, because of the imperfection of the data sets, only 65% of all documents provided by the allometric contain the Scoopers subject list. The list is essential to our program, as we use it to determine the different fields that we can test for interdisciplinarity. This imperfection can potentially create a bias. The solution is to use long short-term memory, or LSTM, which is a recurrent neural network proposed in 1997. We would use this portion with the subject as a training set and be able to accurately generate the Scooper subjects with an abstract of a paper. This is our next step, and I believe that this approach will eliminate potential bias. And also, there's room for improvement for the k-means clustering. Clustering is viewed as an unsupervised method for data analysis. However, one main shortcoming for k-means clustering is that the number of clusters is a parameter that has to be supplied. Additionally, during our research, k-means clustering did not work well on the data that is heavily left skewed due to its inability to partition a compact cluster in certain circumstances. The improvement of the algorithm will be the next step for the project. There are two theoretical means to make this happen. We can either use the Bayes information criterion or the Davis-Borden index to approach it heuristically.
So in conclusion, the statistical analysis has been applied to the allometric data from 2016 to determine how impactful each interdisciplinary field is. By combining the clustering results with the matrix data, we were able to evaluate different interdisciplinary fields in a simple and effective way. The results invoked some interesting thoughts about what intersections are the most impactful. Some overall improvements for the future include improvements in the data and the algorithm to produce more accurate results. Also, we would like to compare the data in 2016 with that in the past to find the changes throughout the years. Thank you.
Any questions?
Any questions? Yeah.
So can you go back on your matrix?
Yeah, sure.
It's a 25-10 matrix, and on the axis, on the rows and columns, you use the indexes, the IDs, right?
Yes.
And what are the values of the entries?
What are the advantages?
Those are the altmetric values of the matrix elements.
For the matrix, we assigned each subject an ID between 0 and 69 just to order them. Or 0 and 20.
Right?
Yeah.
What are the values of the
So it takes the average of all the arithmetic scores that
on that particular field?
for papers that have both the fields, both the column and also the rows.
Okay, so
So we are enumerating